Another week has gone by in Advent of Code, and I wanted to give a quick recap on some of the problems we've worked on since the last video. Day 8 was all about a forest represented as this two-dimensional grid where each digit represented the height of a tree. In part 1, we wanted to find out how many trees were visible by looking from each of the edges. So basically going through these in a straight line, either from left to right, up to down, right to left, or down to up, we wanted to count how many of these numbers were greater than all of the other numbers we've encountered so far. And one of the things we'll need to keep in mind for this is that some of these trees are going to be visible from multiple angles, and we don't want to end up counting them twice. Part 2 is a little different. For each location in the forest, we wanted to calculate a scenic score by looking in all 4 directions and counting how many trees we can see before encountering one that's at least as high as the one in this location. And then we want to multiply those 4 values together, and that's our scenic score. And then we just need to find which location has the highest scenic score. So starting with part 1, since we don't want to double count any of the trees that are visible, we're going to use a set data structure, because as you might remember, a set will naturally disregard any repeat elements. Something we'll have to keep in mind though is because we're dealing with two-dimensional coordinates, we're going to actually convert these to a single number, because otherwise it won't be able to properly compare the arrays to be able to tell which ones are duplicates. So we have this coordinates to hash function, which is going to basically represent the coordinates as a single number so that it can actually tell which ones are equal and therefore avoid repeating them. To count the visible trees from a given angle, we're just going to use this recursive findVisible function, which basically is just going to start at the given coordinates and move in the given direction, keeping track of which tree height has been the tallest so far, and it's going to give back a set containing all of the visible trees in the form of a hash. To get all the visible trees, we're going to go through the whole matrix using a reduce. And basically the idea is that for each row, we're going to call the findVisible function going from the left as well as from the right. And then we're also going to have this nested reduce just for the first row that's going to go through all the columns as well. So it's a little awkward having them both in one like this. We could have done these separately, but this way we only have to do one reduce, so we'll only go through the matrix once. But it's totally up to you if you'd prefer to do these separate. And then we'll just calculate the size of that set since we were looking for the number of visible trees. For part 2, to calculate our scenic score, we have a very similar recursive function to what we started with in part 1, but this one is going to stop as soon as it finds a tree that's at least as tall as the one we started with. And then to get the actual scenic score, we're going to start with our 4 cardinal directions and then reduce those to multiply them all together, starting with a value of 1. And then we'll use another set of nested reduces to go through the whole matrix, find the scenic score for each location, and then just return the highest one of those. And that's part 2. Day 9 was a very unusual and very interesting challenge. Basically, we're looking at a rope that has 2 knots in it, the head knot and the tail knot. And we're pulling the head knot around in various directions, and we need to calculate where the tail knot ends up going. As the head knot gets moved around in 2 dimensions, the tail knot is going to follow it, and we basically just need to make sure that the difference between the 2 knots is not greater than 1 in either dimension. So if the tail knot ends up too far away in one of the dimensions, we'll just move it right behind the head knot. And then part 1 is just asking us how many different points the tail knot will ever end up occupying within the whole motion. Part 2 is basically the same thing, except instead of 2 knots, now we're dealing with 10 knots. So basically we're going to have a head knot, and then a tail knot that follows the head knot, and then another tail knot that follows that tail knot, etc., until we get to the 10th one. And just like in part 1, we're trying to find how many different points the final tail knot is going to occupy. So, similar to the last problem, we're going to be storing a set of coordinates. So we're going to be using this coordinates to hash function so that we can easily store them without repetition. We also have our 4 directions, just like in the last one, but now it's in the form of an object, which we're going to use to help decode the input. I felt like this puzzle really lent itself very well to functional programming because we were able to break up all the different parts into their own functions. So first of all, we have this move point function that we're going to use to move the head knot, and it's just going to give the new coordinates. And then we have a follow point function that we'll use for the tail knot, and then in part 2 that'll be used for all 9 of the tail knots, and we'll basically just specify which point is leading and which point is following. Then we'll just use a bit of math to figure out how we actually want to change the coordinates of the following point, if at all. And what we'll return are the new coordinates of the following point. Then we have this function that's just going to go through all the knots in the rope and update them accordingly. So it starts by moving the head point, then we'll go through this reduce function to go through all of the tail points and reposition those according to our follow point function. We'll update the set of all points that the tail knot has been through in the form of a hash, and then we'll either return those results or we'll run the function again. So this is a recursive function because in our input, we're not just moving the knot one space at a time, we're moving it by multiple units. So that's our update points function. And then our final function is going to run through all of the instructions. It's going to execute them using this update points function. And then finally, it'll return the number of different points that the tail knot moved through. And then the nice thing about that is we can get our results from part 1 and part 2 by just calling the same function with a different number of tail knots. On day 10, our input is this long list of instructions that are basically of the form add x or no op. An add x operation takes 2 cycles to complete and it changes our x value by the specified amount. A no op takes 1 cycle to complete and it does nothing. So for part 1, we basically just want to take the x value that we end up getting after the 20th, 60th, 100th, 140th, 180th, and 220th cycles, multiply them each by their respective cycle number, and then add those all up, and that's going to be our result. So it's a little mysterious what that all represents, but then in part 2 it becomes a lot more clear that what we're actually doing is writing to a display. So the cycle number represents what pixel we're writing to, and then the x value represents the position of a vertical line, where if the current pixel location is close enough to it, so within 1 unit, it's going to write a hashtag, otherwise it's going to write a dot. So that'll give us a 6-row, 40-column display, which should give us some kind of image in the end. With the sample input, it's just going to be this kind of test design, but for the actual puzzle input, it's going to display our answer in the form of an 8-character string. So it's a pretty straightforward challenge. The novelty is really in the form of the output. And that's kind of an Advent of Code classic. They've done this kind of thing in previous years, and they're always a lot of fun. So with the help of this regular expression, we started by going through all of the instructions of the input and using that to make an array representing all of the x value changes for each cycle. So even though that seems like a situation where we could use .map, the output we're looking for is actually a different length from the instructions, because remember, every time we have an add x command, that takes 2 cycles to complete. So we're adding on not just the actual number here, but a 0 as well before it. And by the way, instead of making an array of how the x value is changing on each cycle, we could have just made it an array of what the x value actually is on each cycle. And that actually might have been easier given what we want to do with it afterwards. But anyway, it's up to you. So for part 1, we're using a reduce, and we're doing that partly to actually get the x values on each cycle. And then also in terms of the special cycle numbers that we're looking for, they're like 20, 60, 100, etc. Basically, something we might notice about those is if we divide them by 40, the remainder will be 20. But since the actual cycles are 1-based, but our indices are 0-based, technically in our case it's actually 19. So if cycle mod 40 is 19, we'll add on to our sum. Otherwise, we'll just keep it the same and keep adding up our x values. Part 2 is going to be very similar. We're also using a reduce. We're also adding up the x values, except now we're outputting to this array representing the screen display. So based on the cycle value, we can figure out which row we want to be writing to and which column the pixel should be in. And then we can also figure out what type of pixel to use based on whether it's close enough to the current x value. And then we'll just use that to update the screen, and that's part 2. So using the actual puzzle input, our screen should look something like this. So if we wanted to get really fancy, we could actually write a function that's going to read from this and determine what the 8-character string is, but that's a lot more complicated, and we would kind of need to know what all the characters look like, whereas we only have these 8. Day 11 was about a group of monkeys that have stolen a bunch of our items and they're passing them between each other. For each item, there's a number representing how worried we are about it. So this is quite an original premise. Basically, what it boils down to is each monkey has a set of numbers. On each step, they're going to perform an operation to those numbers, whether it's adding a number, multiplying by a number, or multiplying the number by itself. In part 1, they're going to divide that result by 3. And then they'll test to see if that result is divisible by a given number that's constant to each monkey. And then depending on whether it's divisible or not, that'll determine which monkey they pass to next. So for each monkey, we're going to process each of their items and pass them to whatever monkey we're supposed to. And then we'll go through the rest of the monkeys one at a time, keeping in mind that they may have received other items that have been passed to them during this cycle. For part 1, we're going to go through 20 rounds of this. And then we're going to keep track of how many times each monkey inspected an item. And then whichever of those numbers are the top 2, we're going to multiply those together, and that'll represent the amount of monkey business, which is the result we want to return. For part 2, we're going to keep this going for 10,000 rounds instead of just 20, and we're not going to divide the worriness level by 3, so those numbers are going to get larger and larger, and it's kind of implying in the problem description, we're going to have to find some way to make them not be completely out of control. So in contrast to the previous day's challenge, this one really required some innovative thinking, both in terms of the implementation and the problem solving, which I thought was really neat. So since each monkey is checking for divisibility according to some divisor, we can actually just multiply together all of those divisors and then take the mod of that each time, because that won't change the divisibility, but it'll keep the numbers reasonable. We could also just use big int like we saw in one of the previous problems, but it's kind of overkill for what we need to do in this problem. So I started with this really long regular expression that we're using to get all the relevant information for each monkey. And just as a side note, you might notice I'm extracting the index value but not actually using it. That's because I'm assuming that the indices are starting at 0 and just increasing consecutively, but technically if we don't want to make that assumption, we might want to use the index here. One thing I really liked about doing this in a functional way was that we were basically able to take all of this information and condense it down into these 2 functions that respectively give us the next worry level and the next monkey that we're passing to. So then for each monkey, while we're simulating this, we can just run each of these functions. So we're going to keep track of those functions in an array called monkey info, which is just going to remain constant and unchanged. But then we're also using this very large reducer to calculate where our starting items are, as well as our divisor product that we're going to be using in part 2 to keep all of our worry levels manageable. The idea behind doing it this way is I figure the monkey info remains constant, whereas the locations and worry levels of each item is subject to change. So I just wanted to sort of keep these separate. The next thing is this getNextItems function, which is going to return a new array of arrays representing the locations and worry levels of all of our items. The idea behind this function is that it's going to go through all the items that a single monkey is holding at a time. So we're going through the array representing just the items that the current monkey is holding. Our accumulator is going to be an array of arrays representing the full next list of items. And it's going to start off being basically the same as our items list from the input, except the current monkey's items will be empty because we know we're going to go through all of those and toss them to somebody else. To keep this function reusable, one of the inputs is a Boolean that represents whether or not we should divide by 3. So depending on whether that's set to true, we're either going to divide the new worry level by 3, or we're going to mod it with our divisor product. And we're getting that new worry level by running this monkey's operation function. We'll also use their getNextMonkey function to figure out which monkey to pass to. and then we'll append that item to the target monkey's list of items for the next value of the items accumulator. So that's going to process all the items for one individual monkey, but we want to go through all of them and we want to do it multiple times. So our function for doing that is going to be somewhat complicated. Basically, this is going to do all of that. So this function will take our monkey info and starting items that we got at the start, and then we'll also give it the number of times we want it to go through this, as well as whether or not we want to divide by 3. So that's going to depend on whether it's part 1 or part 2. We're going to start with this range function, which is just a utility function we wrote that's going to make an array of the given length that's just of the form 0, 1, 2, 3, etc., all the way up to, but not including the value cycles. So we're making this range just so that we can run a reduce on it as kind of an alternative to doing a loop, but if you prefer, we could use a recursive function to do the same thing. Our accumulator has 2 parts. The inspections, which is basically the thing that we're trying to figure out, how many times does each monkey inspect an item, and then items, which is going to keep track of where all the items are and what the worry levels are associated with them. So inspections is just going to start as an array, the same length as the number of monkeys we have, starting with all zeros, and then items will start as starting items. And then we have this nested reduce because on each cycle we want to go through each of the monkeys. Of course, every time we process one of the monkey's items, it's going to alter the items that the other monkeys are holding, which is why we need to keep track of our items array also within this reduce. We know that each monkey is always just going to inspect all of the items they're holding, so for the inspections, we're just going to add on the length of the current list of items that that monkey has, and then for the items, we'll call the getNextItems function that we saw above. So then once that's all done, we just need to get the product of the top 2 values in our inspections array. We could do that by sorting the array and then just taking the 0th element and multiplying it by element 1, but just to be slightly more efficient, we've written this getProductOfTop2 function. And it just goes through the array once using a reduce. And then that's actually everything. Because we wrote our functions in kind of a dry way, we can just call the same calculateMonkeyBusiness function for part 1 and for part 2. The only differences being that in part 1, we want 20 rounds and we do want to divide by 3. In part 2, we want 10,000 rounds and we don't want to divide by 3. So that was a bit of a tough one, but we got it done. Day 12 was another pretty classic Advent of Code challenge. We're given a grid of characters that basically represents the elevations on a map, and we need to make it from the start point to the end point by going one step at a time, up, down, left, or right, and the character in the square that we're moving to needs to be at most 1 character greater than our current square. So this is a pretty perfect candidate for a search algorithm. In part 1, we just need to know the minimum number of steps it's going to take to get from the start to the end. And then in part 2, we want to find which point on the map that has a character of A would be closest to the goal. In other words, it would take the least number of steps to get to the end. So since we want to find the minimum number of steps it's going to take, we're going to use breadth first search. If this had been a weighted graph, we might want to use something like Dijkstra's algorithm, but since it's just a 2-dimensional array, all of the edges are considered of equal weight. So breadth first search is a perfect fit. We could also use depth first search instead, and admittedly, it would be a lot more straightforward to do that recursively, but breadth first search is kind of a better fit because 1, we can stop as soon as we reach the goal, since we know that we've done it in the fewest steps, and 2, we never have to revisit nodes since we know there isn't a way to get there in fewer steps. So this is another puzzle where we're going to be keeping track of which 2-dimensional coordinates we've visited. So again, we're going to use this coordinates to hash function that we've used previously, but then we're also going to do this hash to coords function because we might need to convert those back into an array of coordinates. To get set up, I started by converting the puzzle input into a matrix of characters and just replacing the capital S with an A and the capital E with a Z, since that's what they're equivalent to, but they also want to mark the start and end. So then to actually get the start and end, I got those coordinates in the form of a hash by doing another reduce on the input. We could have done these two things in a single reduce, but I think it's just a little more readable this way. Our breadth-first search is a recursive function that takes in a queue of coordinates and a set of visited nodes. The values in the queue will also keep track of how many steps have been taken to reach that point, so we can eventually return that once we reach the goal. Initially, our queue and visited set will just have the starting point, and on each step, we take the first element in the queue, then use a reduce on the 4 directions to get an updated queue and visited set. This is a bit like the way we set up the depth-first search function on our first attempt at the Day 7 challenge. Anyway, this reduce also checks to see if we've found the answer yet. If we found the answer, we'll return it. Otherwise, we'll call the function again with the updated queue and visited set. And that's our breadth-first search. It would probably be a good idea to also put a check to see if there's anything left in the queue, just in case we never actually find the goal, but it's guaranteed for this puzzle input, so I didn't worry about it here. For part 2, since we're looking for the best starting point, we could try running our breadth-first search function on each A character location, but the simplest strategy would just be to run the breadth-first search in reverse, starting at the goal and then ending once we find an A. We could use the same breadth-first search function for both and have some parameters to decide whether we're going forward or in reverse, but I ended up just making a slightly different version of the function since it seemed a little more readable that way. So it's definitely easier to implement breadth-first search in an iterative way, but this is still nice and doable and fun and good. For day 13, we're given a list of pairs of nested arrays representing packets, and we needed to find a way to compare the arrays to tell if they're in the correct order. For part 1, we just wanted to add up the indices of all the ones that are in the correct order. And then in part 2, we want to use our ordering function to see where these 2 new arrays would end up if we added them to the list of all the packets and then sorted them. And then we get the answer by multiplying those indices together. I was expecting that a big part of the challenge would be in converting the string inputs into actual nested arrays. I've done challenges like that in the past, and it can be a bit of a pain to implement. Thankfully, it turns out we can actually just use this JSON.parse function, and it'll do the conversion beautifully. Plus, it doesn't seem to have the same security risks as using the eval function. So from here, we just wrote a recursive function that returns 1 if the arrays are in order, -1 if they're not, and 0 if they're equal. It's a lot of nested conditionals, so it's kind of a pain to look at, but basically we're checking the first element of each array, seeing if they themselves are arrays, comparing the values, and returning the result of calling the function again with the next slice of the arrays if necessary. So with that function implemented, the rest of the challenge is pretty straightforward. We just use the reduce to count up all the indices of pairs that are in the right order for part 1, and then for part 2, I had originally set it up in a more literal implementation where we took the full list of packets, added in the 2 new arrays, sorted it, and then found the indices of those arrays. But it turns out we can actually do this a lot more efficiently by just going through the array once and counting the number of packets that are considered less than each of these new ones, using the same comparing function as in part 1. We start the count of index 2 at 1 since we know we're looking for 1-based indices, and we start the count of index 6 at 2 since we know the other array is always going to be less than this one. And then we just multiply those indices together and we have our result. Oh, and by the way, this .flat function is an array method that we can use to basically remove one level of nesting. So instead of an array of pairs of packets, now it's just an array of all the packets. And that's it for day 13. Day 14 was a simulation puzzle where we basically want to figure out how sand is going to pile up as it falls onto these structures we're given. For part 1, we want to figure out how many grains of sand are going to pile up before they reach a point where they all just start falling off the edge. And then for part 2, we're going to assume that there's a floor at the bottom, and we want to figure out how many grains of sand are going to pile up before the pile actually gets high enough that it reaches the starting point that we're dropping them from. So rather than having like a big matrix representing all of the structures in sand and empty spaces, we're just going to have a set that keeps track of all the points that are occupied by either a structure or a grain of sand. So once again, since we have a set of two-dimensional coordinates, we're going to use this now very familiar function. So we're going to start with just the set of points occupied by structures, and we'll do that by parsing the input and adding a point for each step between the list of given coordinates of each structure. So this is a triple nested reduce. For each structure, we have a list of vertices, and for each set of vertices, we want to basically go from one to the other, adding on a point for each one of those. So that's what our innermost reduce is going to do. Once we have all those points, we can calculate the maximum row that any grain of sand is going to get to before we can consider it having disappeared off the face of the earth. And then we'll also use that to determine where the floor is going to be for part 2. Then we have this recursive function, which is going to actually drop the grain of sand. So technically, it's actually going to take in a set of points and then return a new set of points that includes the location of this new grain of sand. Or it'll just return the original set of points if it doesn't land anywhere. And if the grain of sand hasn't landed yet and it hasn't exceeded the maximum row, we'll call this function again with the new coordinates of where it's going to fall. And then finally, we have this other recursive function that keeps dropping grains of sand until it gets a result back where the set didn't change. So this means that it'll stop if the grain of sand falls off the edge or if the sand is piled up all the way to the top. So conveniently, that means this function will work for both part 1 and part 2. The only difference is that for part 2, we're just going to add on this set of points representing the floor before we call it. So that's actually a fairly straightforward implementation task. The problem is that by doing this functionally, we're going to have so many iterations of the recursive functions that we're going to get a maximum call stack exceeded error. So to avoid that, we're going to use something called tail call optimization, which is why we're using this use strict thing at the top. And basically the idea is that for each of our recursive functions, the recursive call is happening within the return statement without any other operations happening to it. And the way that works is that it's actually going to resolve the current call of the function before activating this next call of the function and putting that onto the call stack. So it keeps the call stack manageable rather than piling up on top of it each time. So that's pretty nice, but the problem is there's actually very little support for tail call optimization. Currently, at the time of this recording, tail call optimization is actually only supported by the Safari browser, as well as some pretty old versions of Node. It's also worth mentioning that the thing that's going to make this actually very, very slow is the fact that we're rebuilding the set of points on each call. So even with the tail call optimization, this is still a really, really slow way of doing it, and there's probably a better way to implement it. Anyway, that's going to be it for me today. I hope your advent of code is going great. Thanks for watching, and remember, the first step is believing you can do it. Bye!